Hello folks, so in this video I want to talk about how we can find horizontal asymptotes. We've talked previously about finding x and y intercepts and about vertical asymptotes as well as removable discontinuities, but we never talked about horizontal asymptotes, and that was because this is pretty easy to find back when our rational functions were a little simpler, but now we're going to take a look at more interesting ones. So let's just define asymptote once more. So an asymptote of some function, so our function of interest is f of x, is some curve which is usually going to be a line, but there are such things as nonlinear asymptotes, where your graph, f of x, gets closer and closer to that curve as x or y, or both, approach infinity. Okay, what does that actually mean? Well, let's take a look here. I'll just draw one example here. We could say, well, here's the one that we've been looking at. And I'll draw, let's say we have a vertical asymptote right here. And we have our horizontal one across the x-axis. And let's suppose that this y coordinate, or sorry, this x coordinate, let's say that's at x equals 3. And this, of course, is at y equals 0. Okay, so we've seen rational functions that look like this purple one. It looks like so. Okay, so if you look at the horizontal asymptote, by the way, this could approach plus or minus infinity. If we look at the horizontal asymptote, what's happening? Well, our graph, which is f of x, gets again closer and closer and closer to y equals 0. Closer and closer as x grows. And that could be going positive or negative. Gets closer to... Now, I know it's awkward to say closer to infinity when infinity is not actually a number, but you understand what I'm saying. It's simply as x gets larger and larger and larger, without bound. The distance between the purple graph and this line, y equals 0, is getting smaller and smaller. Okay, but if we look at a vertical asymptote, just to make sure that our definition fits here, on our vertical asymptote here, our graph, again, gets closer and closer to the graph x equals 2 as, what happens there? Y gets bigger and bigger, gets larger, and again approaches plus or minus infinity. Okay, so we've already talked a lot about vertical asymptotes, so today our focus is on horizontal asymptotes, and I want to compare two functions. Okay, so we'll go over here. Oopsies. We're going to compare a function that we've seen before, f of x is equal to 1 over x plus 2. We'll do minus 2. And g of x is equal to 3x plus 1 over... we'll do x minus 2 again. Right? Okay, so you might notice that both of these graphs are actually going to have horizontal asymptotes at x equals 0. At x equals positive 2. So those will be 2 here. And this graph, well, if x is on the left side of 2, then that denominator is going to be positive. And so as we approach infinity, i.e. plugging in big x values, then we're still going to be positive, but again get closer to 0. And opposite on the left side. Draw that right there. Okay, and this one also has no removable discontinuities. So if you remember, how did I find my horizontal asymptote? Well, I plugged in some arbitrarily big number for f of x. And so when I plug in some big number for x, I essentially get 1 over a big number, which is a small number. Again, very intuitive is how I like to think about this. If you wanted to do it formally, what you're actually doing is this, and it's going to look a little bit fancy. This is you're going to see this in calculus, what is the limit as x gets bigger and bigger, approaches infinity is how you would say this, of f of x. And so that's the limit as x approaches infinity of this function. And what happens? Well, it becomes arbitrarily small, and so what we say is that it equals 0. Because if x is big enough, then that number gets tinier and tinier and tinier, might as well be 0. But it's never actually equal to 0. Okay? So you cannot say that f of x actually equals 0, but you can say it gets closer and closer to 0. Okay? And that's how we're going to find horizontal asymptotes, actually, no matter what the type of function is. Okay, if we compare that to this one, well, we can see here that this function will have a vertical asymptote, excuse me, at x equals 2, just like before. What's interesting about this one is that this one actually does have an x-intercept. And so this one, well, actually, we'll get back to that. I kind of spoiled it, but I'm going to do the same thing to find a horizontal asymptote. Is I'm going to plug in a big value for x. Okay, so what happens here? Well, if I literally just plug it in, I'll get 3 times some big number plus 1 over that big number minus 1. What am I supposed to do with that? Minus 2, excuse me. So what can I do with that? Here's where we get to this really fun part. I think this part is actually one of my favorite things to do with or just function in general. Just use these kind of funky looking things where I just say I just plug in a big number and see what happens. Okay, so if I plug in some big number, let's pretend x is equal to 5. And we're going to compare that to x equals 10,000. If I plug in x equals 5, then f of x is just, let's see, 3 times 5 plus 1, so that'd be 16, over 5 minus 2, which is just 3. If I plug that over here, f of x will be equal to 30,001 over 9,998. Okay. My question is, how important are that plus 1 and minus 2 actually when x is really big? And what I mean by that is, what would happen if it wasn't there? So if I just evaluate this without the plus 1 and minus 2, then I'll simply get, well, I'll get 5. Sorry. Not 5, I should get 3, because it should be like that. Same thing over here, actually. I should get 3 times 10,000 over 10,000. That's going to equal to 3. Okay. But we want to see the effect that the plus 1 and minus 2 actually had. So if you actually incorporate that plus 1 in the numerator, that minus 2 in the denominator, that 3, when you plug in x equals 5, turns into 16 over 3, which is, by the way, 5.3 repeating, 5 1/3. But when I get x to be really, 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 really big, the effect is actually not very significant. Let me actually pull out my calculator to see what this actually is. So after a little bit of calculator work, I have found that this is actually 3.0007. And so we see here, okay, once x is actually really, really big, this might as well be 3. And we can see why, because look, this plus 1 and then minus 2 are tiny, tiny, tiny compared to, again, 10,000. Like so. Okay, so what was the point of this demonstration? Well, what we can say then is that, again, when x is really, really, really big, this function is essentially equal to just this. 3 times that big number, or 3x, over that big number. Remember, these big numbers are the same value. They're both the same x value. And so what we can actually do is simply cancel them out like so. And we're left with 3. And so what do we just find? Well, all of this says that the limit as x approaches infinity of 3x plus 1 over x minus 2 is equal to, well, 3, right? Because again, that those plus 1 and that minus 2 in the numerator denominator are insignificant relatively when x is really, 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 really big. And so you can eventually just eliminate them, and so your resulting value, the resulting y value that this function gets closer and closer to, is the y value y equals 3, which means that our horizontal asymptote is at y equals 3. Okay, so that would mean our graph looks like this. And you could check me, but this graph, other than this fact that for horizontal asymptote is now at y equals 3, has the exact same shape as the typical rational functions we have been looking at. Okay, so this one's going to look like so, and I could just check, by the way, because I could also find my x and y intercepts. I'm not going to go through that at this point. We'll do another example in a later video, but this graph is going to look like so. Okay, so thanks for watching. Hopefully that made sense. Again, the big takeaway for today is using this fact to find a horizontal asymptote. Alrighty, thanks for watching, folks. I'll see you in the next one.